Spot voltage.
Contents. 1. Background. 2. Bath voltage. 3. Problem. 4. Mitigation. 1. Background.
Background. Overall. Equal to. Entry to anode. Plus. Bath. Plus. Bottom, cathode. Plus. Collector bar to exit. Background, target. A equals energy to produce 1 ton aluminum, kilowatt-hour per ton aluminum. U equals spot voltage, V. CE equals current efficiency in percent. Lowering A by reducing U. Contribution to overall voltage from each factors above. Bath equals 80.20%. Anode equals 5.82%. Cathode equals 8.15%. Exit equals 5.82%. In order to get optimum impact, first thing should be thought is to control bath voltage well. Uncontrollable bath voltage make other factors modification will not bring any good at all to overall voltage. Meanwhile, if you have been guaranteed the bath voltage control well, you just can make any modifications to other factors, for example, modifying stub to carbon connection, STC, in order to reduce voltage up to 25 millivolts. Bath voltage is the biggest one. So, talking about energy efficiency means how far your readiness in lowering this voltage.
2. Bath voltage.
Bath voltage consists of ohmic voltage, U ohm, plus electrochemical voltage, U elec. Ohmic voltage consists of omega volt, U omega, plus bubble voltage, U bub. Electrochemical voltage consists of reversible decomposition voltage, A null, plus anodic reaction over voltage, eta AR, plus anodic concentration over voltage, eta CR, plus cathodic concentration over voltage, eta CC. Now, we're going to explain each part in detail and also inviting you to get all opportunities available in order to reduce bath voltage. Ohmic part of the bath voltage. 1. Omega voltage. The voltage loss due to the ohmic resistance of the electrolyte. In order to reduce omega voltage, we should do 1. Lowering anode-cathode distance, ACD, by decreasing PSP. 2. Lowering anodic current density, JA, by enlarged carbon anodes. 3. Increasing electrical conductivity of the electrolyte, kappa, by maintaining bath condition. 2. Bubble voltage, U-bub. The horizontal orientation of the anode in the Hall-he-rolled cell causes gas accumulation beneath the surface, reducing the electrically conducting area. In order to lowering U-bub, things should be done. 1. Thinning bubble layer thickness, D-bub, by suppressing anode effect. 2. Lowering anodic current density, JA, by enlarging carbon anode dimension. 3. Increase electrical conductivity of bath, kappa, by maintaining bath condition. 4. Reducing surface covered with bubble, phi, by making slot on anodes. Electrochemical part of the bath voltage. 1. Reversible decomposition voltage, A null. In order to reduce A null, things should be done. 1. Lowering bath temperature, T, by controlling bath acidity. 2. Reducing alumina oxide concentration in bath applying appropriate feeding system tools. 3. Increasing alumina oxide solubility by synchronizing between hardware and software. 2. Anodic concentration over voltage, ether AC. Due to the slow mass transport of the reacting species, a concentration gradient is built up around the electrodes. The additional concentration over voltage is necessary to make the electroactive species migrate against this concentration gradient. In order to lowering ether AC, things should be done. 1. Lowering bath temperature, T, by maintaining bath acidity. 2. Reducing critical current density, J crit, by enlarging anode dimension. 3. Reducing anodic current density, JA, by enlarging anode dimension. 3. Anodic reaction over voltage, ether AR. The excess applied voltage makes the reactions, especially the electron transfer at the electrodes, proceed at an appropriate speed. In order to decrease ether AR, things should be done. 1. Lowering bath temperature, T, by maintaining bath acidity. 2. Increasing limiting current density, J lim, by enlarging anode dimension. 3. Decreasing anodic current density, JA, by enlarging anode dimension. 4. Cathodic concentration over voltage, ether CC. Due to the slow mass transport of the reacting species, a concentration gradient is built up around the electrodes. The additional concentration over voltage is necessary to make the electroactive species migrate against this concentration gradient. In order to lowering ether CC, things should be done. 1. Lowering bath temperature, T, by maintaining bath acidity. 2. Lowering cryolite ratio, CR, by making up bath. 3. Lowering cathodic current density, JC, by maintaining sidewall. Bath voltage summary. From the previous presentation, the information can be summarized as follows. The three biggest contributors to lowering bath voltage, both ohmic and electrochemical part, are 1. T, bath temperature, 2. Ja, anodic current density, 3. Kappa, bath electrical conductivity. And those can be done by 1. Caring for bath acidity, be always in the control range. 2. Anode enlargement. 3. Keeping bath chemistry in the most suitable condition. 4. Looks, lowering ACD gives only 5.3% contribution, so it is not the main contributor in order to reach the target. The question is, can we make it happen?
Three. Problem.
Philosophically, decreasing the pot voltage, in this case the permanent set point, can be interpreted as an effort to prevent anode effect. The smaller the chance of an anode effect occurring per day, the more stable pot will be got. And in stable condition, it is hoped that productivity will come, more and more reduced metal can be collected, current efficiency rises and net anode consumption goes down. But in fact, the permanent set point has been set up to the extreme value of the pot operation control curve. Looks, slowly but surely the anode effect frequency continues to rise. This means that permanent set point settings cannot be used as a powerful medicine for maintaining stable pot operation. Further in-depth thinking, it could be interpreted that stranding the permanent set point at the extreme values of the operating pot control curve is not recommended if the technology to reduce the magnetic field has not been provided, or vice versa. The technology already exists but the operating pot control program algorithm has not been adapted. Between hardware and software should be well integrated.
Well, that's why lowering the PSP down to its extreme is not recommended if not matching yet, sister. Beware of lowering PSP, ACD. Problem in operation? What the hell is going on? The fact is, anode effect frequency has a tendency to rise. Why? Are there any problems in charging the alumina properly? By the way, only a little is within the control range. The fact is, bath temperature has a tendency to rise. Why? Are there any difficulties in charging the aluminium fluoride properly? 4. Mitigation. Mitigation, come on guys. The target and all the root causes have been explained. Are you still blaming the anode to cover up the real problem? Ouch, come on, cheer up, be on fire, guys. Integration between hardware and software is absolute. It has been proven that even though the hardware has been modified, the software cannot be improved. So you can only try and get the right settings, the results are not optimal. Think about changing software. Temperature is one of the important control items which in reality has been proven that it cannot be kept low, within the control range, and has an upward trend. Whether you like it or not, you have to start reviewing the formulation and dosage of aluminium fluoride charging. Is it true that what we have now? The anode effect has an upward trend. What is this? We all know that anode effect events should be suppressed as rarely as possible. If the hope is to simply make the ACD as low as possible by modifying the permanent set point, PSP, parameters without solving the main problem, namely the feeding process, it will be in vain. Come on guys, you can do it. You are all masters at this. 274. Can you? You can.
Thank you.